So we've looked at the idea of stability and how to analyze stability using energy principles using the simple example of a bead sliding on a wire. Now we apply these ideas to buckling problems. So consider a cantilever column. When a large enough axial compression is applied to the cantilever column, we know that it will buckle. So we seek to understand this process qualitatively using an approximate model to which we'll apply our energy principles from the last video. We'll see that the concept of buckling actually relates to transition of an equilibrium point from being stable to being unstable. Therefore, because it's an issue of stability, we can explore this using the energy principles that we motivated using the bead example in the last video. So let's build this very simple approximate model of a cantilever column. This model, we call this the toy column model. This model consists of a rigid bar held below by a rotational spring whose spring constant, K, is a moment per unit rotation. So it could have units like pound inches per radian. And the height of the column is L. Now suppose this column buckles and is in a non-vertical equilibrium position. Let's draw a free body diagram in this non-vertical equilibrium position. Let's say the orientation is theta, the load P, reactions at the pin Rx and Ry, and the resistance from the rotational spring, which is K theta. So let's do some of the moments about this bottom point O. We get K theta minus PL sine theta equals 0. From this, we see that theta equals 0 is always a solution because theta equals 0 solves the equilibrium equation. This means the vertical position is always an equilibrium point. Now we ask the question, when is a non-equilibrium position possible? So the equilibrium equation K theta minus PL sine theta equals 0 can be rewritten as K divided by PL times theta equals sine theta. So let's draw the two curves, the sine theta curve, and the straight line K divided by PL times theta, whose slope is K divided by PL. So for the line to intersect the graph of the sine curve at points other than theta equals 0, the slope of the line must be less than the slope of the sine curve at theta equals 0. This means the slope K over PL must be less than 1. Or in other words, P must be greater than K over L. So we see that the critical load, P critical, equals K over L. So if P is more than P critical, then a non-vertical equilibrium position is possible. And for P less than P critical, only a vertical equilibrium position is possible. And therefore, this P critical is the buckling load. So if we plotted P versus theta, until P equals P critical, only vertical equilibrium points are possible. For P greater than P critical, vertical as well as non-vertical equilibrium positions are possible, as shown in this plot. So for P less than P critical, there's only one equilibrium point, namely the vertical equilibrium. And then for P greater than P critical, there is the vertical equilibrium as well as an equilibrium point deflected to the right, an equilibrium point deflected to the left. Now let's try to apply the energy principles from the bead example. So the energy, just like the total energy in this toy column, the energy stored in the spring is 1/2 K theta squared. You've probably seen this kind of thing in mechanics of solids, undergraduate mechanics of solids. Now think of P as a weight. So the gravitational potential energy of P is simply the weight times the height, and the height is L cosine theta. So the energy of the load is simply PL cosine theta. So the total potential energy of the toy column, which we call V of theta, is 1/2 k theta squared from the spring plus PL cosine theta from the load. Now let's write V prime of theta. We see that that is nothing but the equilibrium equation. Setting V prime of theta equals 0 gives us the equilibrium equation identical to what we obtained using the free body diagram. Now we saw in the bead example that V double prime tells us something about stability. So let's look at V double prime of theta, which is equal to V double prime of theta equals K minus PL cosine theta. And we consider two cases, P less than K over L, when the only solution is theta equals 0, and K minus PL is greater than 0. So that's stable equilibrium point. So for P less than P critical, the vertical equilibrium is stable. When P greater than P critical, there are now two possibilities, theta equal to 0 and theta not equal to 0. When theta is equal to 0, you can check that V double prime of 0 is actually less than 0. So vertical equilibrium is unstable for P greater than K over L. For theta not equal to 0, you can see the attached MATLAB live script, which demonstrates that V double prime of theta is greater than 0. So the non-vertical equilibrium points are stable. So let's mark these things on the curve above. So for P less than P critical, or before buckling, the vertical equilibrium position is stable. After buckling, the vertical equilibrium position is unstable, whereas the two non-vertical equilibrium positions are stable. So what happens after the buckling load is called post-buckling behavior.